So, let us do the Dyson's equation for the Matsubara Green's functions. So, this is in line with what we have done for the 0 temperature Green's function. So, from the discussion so far, it is evident that the Matsubara Green's function formally looks similar to the 0 temperature Green's functions, excepting that now we are talking about a complex time being bounded by minus beta to plus beta, and the information about the temperature enters through the quantization of the frequencies. And in case of fermions, the frequencies are quantized in odd multiples of pi over beta, and for the bosons they are quantized in terms of even multiples of pi over beta. So, we need to now write down a Dyson's equation in which we want to avoid doing a finite order perturbation theory and want to invoke all orders of H prime into the sum, and we have seen that this is quite a doable exercise. So, consider the Green's function. G k, the k's are vectors, but since we have not been putting, so let us just remove this, and t tau is what we have seen. It is a minus beta omega, and then there is a trace exponential minus beta k, the tau and exponential tau k, c k sigma exponential minus tau k, c k sigma dagger, and that is the expression for the Matsubara Green's function. Just to remind you that we are writing it with a calligraphic G. Omega is the grand potential, and k is given by h minus mu n, and exponential minus beta omega is equal to trace of exponential minus beta k. So, this is something that we have seen, and k equal to h 0 minus mu n plus v, where v is the potential which typically represents a two body interaction term. Say it can represent an electron-electron interaction of the Coulomb type, which is what we have been most familiar with. So, now so the k 0 problem, that is this part has already been solved. So, this is the k 0. So, suppose we have been able to solve this exactly, that is without the interaction term, it has been solved exactly, and also that our these h 0 commutes with the number operator, and so does the total h, which includes h naught plus v with the number operator that commutes, and so the eigenstates of the number operator are simultaneous eigenstates of both h 0 and h. So, let us write down the operators in the interaction representation. and write those unitary operators which we have introduced earlier, but with real time as exponential tau k 0 and exponential tau k. If you remember that we have written down similar operators with I t and with h 0, and so this is not h, but we will write it as k. We had written it earlier for the 0 temperature problem with tau as I t and k zeros as h 0 and k as h, and so on. Similarly, we would have u inverse tau, which is equal to exponential tau k exponential tau k 0. Needless to say that k and k 0 do not commute. I mean, rather there is a part of k 0 which does not commute, there is a part of k which does not commute with k 0. So, as we have written it earlier, the operators can be written as c k sigma tau, which is equal to exponential tau k 0 epsilon k sigma exponential minus tau k 0, which is equal to exponential psi k tau and c k sigma. This has been proved earlier, that is the tau evolution of the, or the imaginary time evolution of the operators, and hence we can put them into the this g k tau, which is equal to exponential minus beta omega and then a trace of exponential minus beta k 0. We have just introduced exponential beta k 0, exponential minus beta k. So, we have introduced this exponential minus beta 0 and exponential plus beta 0, and then exponential tau k exponential minus tau k 0, and again we have exponential tau k 0 c k sigma exponential minus tau k 0 exponential tau k 0 exponential minus tau k and a c k sigma dagger. That is our Green's function, and this can be written as we have a minus trace of exponential minus beta k 0 u of beta. See the definition of u here, it is exponential tau k 0 and exponential minus tau k. So, that is written here as u of beta. So, the whole idea of writing it into this, in this particular form, is to introduce these u operators, and then you have a u inverse tau and a c k sigma tau and a u tau and a c k sigma dagger, and this is divided by trace of exponential minus beta k 0 u of beta. Just show in a moment that how this thing comes. So, we have u exponential minus beta omega that can be written as trace of exponential minus beta k. Now, I will introduce this factor of exponential beta k 0 and exponential minus beta k 0. So, this is trace of exponential minus beta k 0 and exponential beta k 0 exponential minus beta k, and this is equal to trace of exponential minus beta k 0 u of beta. So, a similar substitution can also be has also been made in the numerator for the exponential minus beta k, and that is how this exponential minus beta omega is replaced by trace of exponential minus beta k 0 u of beta in the denominator. So, the equation of motion which in short we will call as UM, can be for u of eta can be written as del tau u of tau will have to, there are two factors in u consisting of exponential tau k 0 and exponential minus tau k. So, one has to be kept constant, the other will be differentiated, and vice versa will have to be done, and in which case we can write this as exponential tau k 0 with a k 0 minus k exponential minus tau k, and we know k 0 minus k is nothing but it is equal to minus of h prime, and this is equal to minus of exponential tau k 0 h prime exponential tau k. So, del tau of u tau, which is precisely the equation of motion, can be written as exponential tau k 0 h prime exponential tau k 0 exponential tau k 0 and exponential tau k. So, this part has been introduced, and such that we can write this as a minus h prime t, sorry, not t, but this will be tau, this tau and u of tau. So, we have seen this kind of an equation. We can write down the equation of this differential, or the solution of this differential equation, as t tau exponential minus 0 to tau h prime tau d tau prime. So, this is the solution of the unitary operator that we have introduced, and all these discussions are simply complementary to the ones that we have done for t equal to 0. So, this is the solution for u of tau. Similarly, we can write it for the S matrix. S tau 1 tau 2 equal to t tau exponential minus tau 1 tau 2 d tau prime h prime tau prime, and so that is the definition of S matrix. Other properties of S matrix: that includes that S tau 2 tau 1 can be written in terms of the u operators like u inverse tau 1, and also the tau 3 tau 2 and multiplied by tau 2 tau 1 will combine to give tau 3 tau 1. All these properties we have seen for the S matrix. So, with all these inputs, we can write down the Green's function as k tau, this is equal to minus trace of exponential minus beta k 0 t tau s beta tau c k sigma tau s tau c k sigma dagger tau, and sorry, this will be 0 and it have the denominator comprising of exponential minus beta k 0 s of beta and so on. So, at the end what is going to happen is that the disconnected diagrams, as we have seen, are going to cancel with the denominator and will be left with only the numerator, and in which case the g k tau is equal to a minus n equal to 0 to infinity minus 1 to the power n 0 to beta d tau 1 and so on 0 to beta d tau n, and we have a t tau c k sigma tau h prime tau 1 and all the way till h prime tau n c k sigma dagger 0. So, that angular bracket is closing. So, this is the expression for the full Green's function, including all the all orders of the interaction term h prime. As we told that the h prime could be of the Coulomb type or for that matter any other type, and we are uncommitted about the nature of the interaction, but if there is an interaction electron interaction in the system, the full Green's function Matsubara Green's function will be like this, where as you n equal to 0 will be the 0th order, 0 and 1 will be till the first order and so on. So, we can take do a perturbation theory in terms of h prime and can write down a Green's function to a particular order that is desirable to us. Now, the question is that if for a given problem doing a perturbation theory up to a given order is not a satisfactory treatment of the problem. It could happen that there are suppose one takes care up to second order of h prime, and then it turns out that the third order is equally important as the second order, and the fourth order could be as important or at least half as important as the third order and so on. In which case we have to go to higher orders, and in principle we have to include all orders of h prime and write down a Dyson like equation, and this is what we are planning to do here. So, just to say that in this particular things only the connected diagrams survive. All right. So, now using the Fourier transform, g k I omega n, this is equal to 0 to beta d tau and exponential I omega n tau and g k tau. So, we will use this Fourier transform, and of course, knowing fully well that my omega n is 2 n plus 1 pi over beta. So, that is the how the frequencies are quantized in odd multiples of pi over beta. So, we write down Dyson's equation as g k I omega n. This is now we do a Fourier transform of this, and then this is written as g 0 k I omega n divided by 1 minus g 0 k I omega n and the sigma k I omega n. So, it is exactly a similar expression we have seen, which we have derived for the 0 temperature Green's function, sigma being the self energy, and for a particular case we have also seen how to compute the self energy. All these rules of writing down the diagrams, or rather sketching down the diagrams and getting out information about the scattering process follows exactly in the same manner that we have seen. So, the rules, just to give you once again the rules is that with each electron line attach G0. The interaction is represented by a wiggly line. Conserve momentum and frequency at each vertex, and also do not forget that the fermion frequencies are odd multiples of pi by beta, whereas the boson frequencies are even multiples of pi by beta, or we can write it as I pi by beta. So, having done this formally, let us try to do one example with the Matsubara Green's function and see that how it enriches our understanding of problems in condensed matter physics. In principle, disorder or defects is indispensable in condensed matter systems. So, these are necessarily present, and even if one tries to make an ultra clean sample, these are always there, and they constantly affect the experimental results depending on the degree at which they are present. Sometimes they are necessary, like in quantum Hall effect, they are absolutely necessary to have the Hall plateaus to be quantized either in integer or in some chosen rational fraction of the quantity E square over H, and sometimes they are non-desirable altogether. In any case, we will do an example of this kind, but before that let us do the equation of motion of the Matsubara Green's function. All right. So, we can take this k prime and tau. We can keep one index for the momentum, or we can keep two indices, it does not matter. Let us just for generality, let us take two indices, and these are t tau, c k tau, just dropping the spin index for the moment, one can put it back, and a c k dagger 0, c k prime dagger 0, and the angular bracket closes here. Now, differentiating with respect to tau, we have d dt equal to a minus d dt of. Now, this time ordering, as we know, that can be easily replaced by the theta function. So, we will do that. Theta of tau c k tau c k prime dagger 0 and minus theta of tau, we have been writing it as capital theta. Let us write it a little neatly here. And of minus tau, and we have a c k prime dagger 0 c k tau, this thing closes and the bracket closes as well. So, these are the two terms. Now, to remind you that the derivative, so this is not d dt, this is d d tau, and the derivative of a theta function is a delta function. So, we have minus delta tau delta k k prime. Now, that comes because delta tau gives me tau equal to 0, in which they become equal time Green's function. So, they will have to have delta k k prime, otherwise this angular bracket will become equal to 0. This is all what we have learned when we were dealing with fermion operators. Minus theta of tau, and these are, I am writing down for the time derivative to be in terms of the equation of motion of each of the operators, which are h this c k tau c k tau and a c k prime dagger 0 this, and then there will be a term which is minus theta of minus tau, and this we have a c k prime dagger 0 and h c k tau and so on. So, we have used d c k tau dt to be the equation of motion for which is h c k tau, where h is the total Hamiltonian for the system, including the h 0 and a v. We have not taken for no particular reason, though we have not taken the k here, but you could just write down k instead of h without any difficulty. So, minus so there are two minus signs. So, we will absorb that and write down the left hand side with a minus sign. So, this is k prime tau, it is equal to delta tau delta k prime plus a t tau h c k tau c k prime dagger 0 and this with another bracket closing here. Let me just do it. So, the important thing is that if H or K for that matter contains interaction term as Coulomb term, okay, which is a 4 operator term or a 2 body term, then this side, that is this one, will involve. So, H contains a 4 operator term and we are taking commutation with C k. So, this will involve higher order Green's function such as 2 particle Green's function. So, when you try to write down the equation of motion for 2 particle Green's function here, it goes and demands that the knowledge of a larger particle Green's function, that is a 3 particle Green's function, etc., that should be available, and then a 3 particle the equation of motion for a 3 particle Green's function would require even higher particle Green's function. However, there is a way to terminate that series. We are not going to discuss that here. For our case, it is sufficient to talk about that, let us suppose H is only quadratic having a form. So, we are not talking about interaction terms immediately, let us just start with the free particle ones. So, it is quadratic in electron operators, and it has a form which is H equal to sum over k k prime and H 0 k k prime C k prime dagger C k C k. So, this gives that the H acting on C k tau gives me that minus k prime H 0 k k prime and a C k prime tau. That is the that is what is given by the commutation of H with C k tau, which you can check easily. Let us do that here. So, H C k tau minus C k tau H. So, this is the meaning of H and C k tau. So, this is equal to C k tau H, and this is equal to C k dagger C k and a C k dagger C k, that kind of a term, and of course, this is equal to 0 because there are two annihilation operators. While one can write this down, change the order and write it as 1 minus C k dagger C k. So, C k will multiply with 1 and give me a C k, and again C k dagger C k will give me 0, and this will give me simply a C k, and that is what is written there. So, the equation of motion yields so we will write it as EOM as an abbreviation for the equation of motion. So, the equation of motion is d d tau of g k k prime tau, which is equal to delta tau delta k k prime plus sum over k double prime H 0 k k prime g k prime k double prime k prime and tau. So, that is the form of the Green's function or the equation of motion of the Green's function. The first term contains just the delta function, which is operative at tau equal to 0, and it is a diagonal term, such that if k becomes equal to does not become equal to k prime, then that term cancels out, and the other one is the off diagonal term. Now, let us imagine that H 0 k k prime contains a diagonal part which is epsilon k delta k k prime, and plus an off diagonal part which is given by V k k prime, which means this is the diagonal term and this is the off diagonal term. Why we are doing this? We want to see the disorder effects which would be included through the second term, which is off diagonal, and the kinetic energy is actually the diagonal term. Now, the equation of motion is written as minus d dt, or rather tau minus psi k and k prime tau. This is equal to delta tau delta k prime and plus phi k double prime and g k prime k tau. So, that is the equation of motion for the Hamiltonian to have a diagonal term as well as an off diagonal term. As I told, the diagonal term corresponds to say operators such as kinetic energy, whereas the off diagonal terms can denote quantities such as disorder or defects in the problem. So, this is my equation of motion. Now, this differential equation can be converted into an algebraic equation. Into an algebraic equation by using Fourier transforms. And what do I mean by that? That is so, I have g k prime tau, it is equal to 1 over beta sum over omega n exponential minus omega n tau and a g k prime I omega n. So, this is the Fourier transform that we have, and the inverse Fourier transform is k prime I omega n equal to 0 to beta d tau exponential I omega n tau g k prime tau. So, you see the g k prime tau is has a Fourier transform in terms of the g k prime I omega n. Omega n's are 2 pi n I pi over beta. So, now what we can do is that we multiply both sides, by exponential I omega m tau and integrate tau from 0 to beta, which yields I omega m minus psi k, or it could be here, as we have not introduced the mu explicitly, we can write it as epsilon k g k prime I omega m equal to delta k prime, that is the first term, and there is a second term which consists of the off diagonal terms, which is v k double prime k and g k double prime k prime I omega m. So, that is what comes when you multiply it by exponential I omega m tau and integrate from 0 to beta, and then we have used here g 0 we have used 1 over beta 0 to beta d tau exponential I p m minus p n tau equal to delta m n, and exponential beta d tau exponential I p m tau delta tau, which is equal to 1. Now, we know that G 0 k I p m, which is here we are writing it as omega m equal to I omega m minus psi k. So, then the full Green's function is written as g k k prime I omega m equal to g 0 k I omega m delta k k prime plus g 0 k I omega m, and there is a sum over k double prime, and there is a v k k double prime, and there is a g k double prime k 1 I omega m. There is a sum over, so there is a k double prime and a k prime. So, this is the form of the Green's function when we have the Hamiltonian contains a term which is diagonal in k, and there is also an off diagonal terms in k. Though we are saying k, we really mean any quantum numbers which is suitable for the which forms a suitable basis for the problem. Will have, so there could be a lambda and lambda prime in principle, which would the calculation would go through exactly. Now, you see that both the sides depend on I omega m. Since both sides depend on a single variable, at so at a particular value of the variable, they will all I mean this equation will be valid. So, that tells that I can actually drop I omega m, it is not required to keep it. So, in both the sides, and we can write down this as an infinite series. So, drop I omega m and write down g k k prime equal to g 0 k delta k k prime plus g 0 k v k k prime k double prime g 0 k prime k I omega m. So, that is the Green's function that we write. We can propose a solution of the type in terms of an infinite series and which is of the form that g k k prime equal to sum over n equal to 0 to infinity g n k k prime. And so, if all the off diagonal elements vanish, so this is the first approximation, if all the off diagonal elements vanish, then we have the g k k prime equal to g 0 k delta k k prime. So, when we have no off diagonal elements, only diagonal elements, the solution of the Green's function is purely the unperturbed Green's function. So, the solution So, now if we insert this solution that we have written here into the equation that is here. So, if we insert one into another, then we can iterate the solution and take out the 0th order, because we have already written the 0th order. So, a g n k prime equal to a g 0. Okay, so this is the full solution. I am writing it down. It's k, and then there is a k double prime v k prime g n minus 1 k prime k double prime k prime, and this is for n greater than equal to 1. So, n equal to 0 is taken out. So, if we iterate this, then what we get is the following. So, the first order k prime equal to g 0 and k and a v k prime g 0 k prime, and a g 2 k prime equal to a sum over k 1 g 0 k v k 1. V is the term that we have taken as the off diagonal term here. So, v k 1, there is a g 0 k 1 v k 1 k prime g 0 k prime, and so on. There will be g 2 and g 3 and so on. So, for a general n, one can write g n k prime equal to k 1, k 2 and all that, excepting the k will reserve. So, these are all will be summed over, and there is a g 0 k, then there is a v k 1 g 0 k 1, and going all the way up to all these g zeros k n minus 1 v k n minus 1 and k prime, and now you have a g 0 k prime. So, at the nth order, we are simply able to write this as n non-interacting Green's function. So, that which are solvable or which can be found out, or we have already found them out, which is like I omega m minus I k. So, all these things, so depends on which order one wants, one can find out this Green's function till the nth order. If you want it till the first order or the second order, you simply need to plug in these v k k 1 or v k k 2, whichever the diagonal terms are, and these are the non-interacting Green's function, which we have already have learned how to write them. So, this is the pretty much the solution for this problem, in which we are simply talking about, still not talking about the interaction term, but talking about the Hamiltonian being quadratic in terms of the operators. What are these calculations good for? Let us apply them to a disorder potential. So, what it means is that at every lattice site, there is a potential which could be randomly varying from one lattice site to another lattice site. So, which could be purely random, or which could be correlated, but this denotes an extra bit of potential at each lattice site, and this could be written as a V of r, which is equal to sum over j 1 to n u r minus r j. So, what we did is that we have taken u to be the potential, and there are j such disorder sites where the potentials are present. So, which are given by all these r u r minus r j, and then when we sum over all these n sites which have all these disorder potentials, we get the total disorder potential, which is given by V of r. So, V of r is the total impurity potential, impurity or disorder, whatever you want to call it. Since we are talking about discrete lattice sites, so it is impurity is a more appropriate word in this context. From n static impurities distributed over j. So, clearly V is not diagonal in the k basis. Okay. And how do we know that? We can write down V, which is equal to a k prime V of r k, and this would give me a ck dagger ck prime dagger ck. So, this is the kind of potential that we were talking about in our previous discussion when we spoke about off diagonal term in the Hamiltonian. It is still non-interacting, but there is an off diagonal term in the Hamiltonian, which is something similar to that. So, what is this matrix element? This matrix element is given by k prime V of r k. Now, there will be when you convert this the expectation into integrations, we will have so 1 over volume, we will have to normalize it with the volume, and there are n such impurities, and we are say talking about 3 dimensions. In principle, we can talk about d dimensions here. So, it is a d cube r and an exponential I k prime minus k. Now, we will have to all put the vectors there because it is a product there. So, u r minus r j and so let us assume that this is equal to a dummy r prime. So, if r equal r minus r j is equal to r prime, r becomes equal to r prime plus r j, and then this becomes equal to 1 by volume sum over j from 1 to n d cube r prime an exponential I k prime minus k r. We are just removing the vector signs, knowing fully well that okay, let us put this just to have completeness, and u of r prime and an exponential minus I k prime minus k dot r j, where r j are the impurity sites. This is, of course, you see that this is independent of j, which means the impurity sites, and we can simply write this as u k prime minus k rho k prime minus k, where u of k is equal to 1 over volume and d cube r 1 minus I k dot r u of r. So, this is the Fourier transform of this impurity potential, and rho of k, which is simply equal to a sum over j equal to 1 to n exponential minus I k dot r j, which gives the concentration or the density of the impurities. So, it is clear that that in this problem we have a v k k prime equal to u k minus k prime minus k rho k prime minus k, which is the off diagonal contribution. And in which case we have g k k prime, which can be written as n equal to 0 to infinity, just like what we have done before, and k k prime, that is the solution, and where g n k k prime, that is the nth order, can be written as sum over k 1 and g 0 u k minus k 1 rho k minus k 1 g 0 k 1 and all that other terms with k 2 for the second order and for the third order and so on. So, one can iterate this solution, but in the first order this is the contribution coming from the off diagonal term, which comes specifically from disorder. So, we have been able to write down a Green's function or a Matsubara Green's function for the impurity problem. Okay. So, this is one of the examples that we wanted to do with the Matsubara Green's function. Rest of the calculations, as we have said, exactly follows that of the t equal to 0. Now, the only difference being that there we have dealt with temperature and frequencies. Now, here we would deal with complex time and complex frequencies, which are having complex values, and the temperature information actually enters through the frequency terms.